So, Chapter 18, Electrochemistry. There isn't a whole lot of info in here, but the first couple lectures are going to be quite long because they really have to be covered all at once. So, we know how to balance oxidation-reduction reactions. We did that way back in Chapter 4. We did them in neutral solutions. Balancing them in acidic or basic solutions really isn't all that much different. Okay, so we go back to balancing an oxidation-reduction reaction, and so this is Chapter 18, Electrochem. This is not going to be on the AP test, but you will have to know it for college. So we've got manganese, or permanganate, aqueous, and iron, 2+, in a solution, generating manganese +2 and iron. Okay. AQ, AQ. Okay, so let's balance this reaction. Now remember, the first thing you do is to balance everything. Well, first of all, assign the oxidation numbers. So let's go ahead and assign the oxidation numbers. So oxygen is -2, which means my manganese would have to be a +7. My iron is +2, so it would mean that it would be that. This one would have to be, since it's a 2+, it'd have to be a +2, and then my iron would have to be, all right, there, whoops. All right, so we have our oxidation numbers assigned, okay? After you do that, you balance, you identify who's the reduction, who's the oxidation. So the reduction is the manganese. Okay? The oxidation is the iron. Balance everything except the oxygens and the hydrogens. Okay? So I can only balance using the things available to me. So to balance the manganese, I'm going to do that. Then I balance everything except oxygen and hydrogen. So then we balance the oxygen with water. So I've got 4 oxygens over there, so I'm going to need 4 waters over here. Okay? Then we balance the hydrogens with H+. So I've got 8 hydrogens on the right side, so I'm going to need 8 H+'s on the left side. Okay, and then the fourth thing you do is balance the charge with electrons. Okay, so this will be an instance where we might have a charge when we're all said and done. So on the left side, I've got 8 positive charges and 1 negative charge. So that gives me a total of 7+ on this side. Okay. On the other side, I've got a +2. So that means I'm going to have to add 5 electrons to this side, because 5 electrons and 7 positive charges gives me an overall charge a +2. Okay? So the number of electrons and the number of hydrogens don't always have to be the same. Okay? Now, in the past, we did problems like this, where the hydrogens and the electrons were the same, but I told you they don't have to be. Okay? So you all have to make sure that the charge is the same on both sides. So if I have a +2 on this side, I must have a +2 on the other side. So, like I said, we need 5 electrons to balance it. Okay? Just going to clean this up. So we need 2 electrons on that side. Okay? The iron, to balance it, we're going to need this. So that's easy. There are no oxygens to balance, so that's good. No hydrogens to balance, so that's good. So all we have to do is balance the charge. I'll need one electron there, because a -1 and a +3 give me a 2+. That balances with a 2+ on that side. Once you have your half reactions, then you have to balance the electrons. So I've got 2 electrons on I've got 2 electrons on this side and only 1 on this side. So that means I have to multiply this side through by 2. So this becomes 2, 2, and 2. And now my reaction is balanced, okay? If I were to add it up, but I really don't care to, well, I guess I'm going to do it anyhow. 8 Okay, because there is H pluses here, this is called balancing in acid, okay? It's nothing really special, it's just that if at the end there's H pluses present, it's called balancing in acid. So if the problem says to balance it in acid, all you're doing is balancing the problem, and you're just going to be left with H pluses at the end, okay? Now, what we're going to do is we're going to take the property of that the electrons want to go from the iron to the manganese, okay? When we look at the charges up here, or the oxidation, it went from a +7 to a +2. How did it do that? Well, it did that because the iron was transferring electrons to the manganese, okay? That's why the charge on the iron went up and the charge on the manganese went down, because electrons were being transferred, okay? We're going to take advantage of that desire of the electrons to go from one to the other. The fancy word for that is electrochemical potential. Can we all say that together? Electrochemical potential. All right, so what we're going to do then is we're going to put these 2 half reactions in 2 separate beakers. This is going to be a big picture, so use a lot of space. It doesn't matter which half reaction you put in which one, but I'm going to put the reduction over here. Whoops. Okay, I'm just putting that half reaction there. The other half reaction goes in the other beaker. Now remember, we said the electrons wanted to go to the manganese, but they are now separated. So what I could do is I could connect these 2 containers with a wire. So I'm going to do that. Now the electrons can flow through the wire that direction, okay? We call the reduction the cathode, and the oxidation, the anode. I spelled anode wrong. Okay, so the way you can remember this is reduction starts with the letter R, and oxidation, I screwed it up. Reduction starts with the letter R, and oxidation starts with the letter O. So the oxidation is the anode and the reduction is the cathode. So you put the consonants together and you put the vowels together. So at the anode, oxidation occurs. At the cathode, reduction occurs. Okay? I'm going to need that space. Okay. So this little square that I drew here, that's an electrode. And this electrode is the anode. Okay, so that's the electrode. There are two electrodes. There's the anode and there's the cathode. Okay, so the cathode is over here. Now, you typically pick a metal that matches your metal that's being reduced. So normally you might pick your anode to be made out of iron. But the only problem with picking your anode out of iron is iron rusts. So you put your iron cathode into water, it's going to rust away. So we are not going to make our cathode or anode out of iron. We are going to make it out of something that doesn't rust, like platinum. That's always a safe bet. But if, let's say, you were doing a copper reduction, you might make your anode out of copper. If you were doing a silver reduction, you might make your anode out of silver. But we can't use iron because iron would rust. Similarly, over here, manganese is not really a good option because manganese is brittle and cracks, so we are going to make our cathode out of platinum as well. Okay? So the electrons will travel over there. Now, at the anode, this is the following reaction that will occur. Okay? Actually, let's make let's just switch it up. Let's make this out of copper. You could make it out of platinum, but I want to try making it out of copper. Okay? Copper doesn't rust either. So the electrons are going into the anode. Okay? The way you can kind of think of it is like this. All right? If the electrons are leaving the platinum anode, you've got this reaction occurring. I ran out of room. So this reaction is occurring on that anode. The platinum is turning into +2. Okay? Now, the electrons from the iron will turn the platinum +2 back into platinum. So basically, the electrons are leaving here, turning this into +2, but then electrons are entering from the iron, turning it back into platinum. Okay? So, oh, shnikes. There we go. All right. On the other side, you've got electrons coming into the copper. Okay, well, you know, metals don't form negative charges. So what's going on over here is that the electrons are leaving the solid copper. So at my cathode, this is occurring. And then these electrons are going down there to react with the manganese. So at this cathode is where this reaction is occurring. Okay, so on that cathode is where that reaction is occurring. All right? So the problem here is that you are getting a bunch of electrons building up in this solution. So this is going to begin to develop a large negative charge, okay? Well, your electrons are going to stop flowing this direction if there's a large negative charge building up, because like charges repel. So what would happen here is you get a current very quickly, and then it would shut off very quickly. So this goes back to the early 1900s when they were trying to develop batteries, and they knew that if you separated the reduction from the oxidation, you could get an electrical current to flow, okay? But they knew that electrical current would quickly stop running because there is a buildup of negative charge. So what can we do to keep that flow going? Well, that's where we introduce what's called a salt bridge, okay? So now, a salt bridge is, we're using the chemist term of salt, which means any ionic compound, okay? So I'm going to use sodium nitrate, but I could use any salt. Some just are easier to work with than others. So I'm going to use sodium nitrate. And the reason why we use a salt is because salts are aqueous in water. And so what happens is the sodium ions migrate over here to balance out the negative charge that is building up from the electrons flowing into the solution. On the opposite side, the nitrate migrates into this solution to balance out the positive charge that is developing in this solution from the electrons rapidly leaving. So what you have here is a battery. You have an oxidation and reduction, and the electrons are flowing through that wire. You have created a current, okay? And that's what a battery does, is it puts the oxidation and reduction reactions in separate containers, and then it allows the electricity to flow through when you plug it into a machine, okay? I am going to pause here and make a second video because we're already at 20 minutes, okay? But I will be continuing on with this discussion.